Okay, so the contents of the talk is so that after we talk a little bit about some basics about RF transceiver impairments, not much detail, some very basic things, I focus mainly on the key points on how these different impairments behave in beamforming arrays. So what kind of spatial properties they may have. And we mainly focus on talking about nonlinear distortion of power amplifiers, because that's something we have been working a lot in the past here. We also talk about this kind of array level linearization. And in the end of the talk, there are some small examples also about other impairments, but the focus is in the PA nonlinear distortion. So that kind of aspects, and there's maybe one conclusion in the end, but only one, so not so many. But let's see. So RF impairments, this could be presented in many ways, but if we think about in general, especially in the higher frequencies, we usually have multi-antenna transceivers, multiple antennas at the transmitter, usually multiple antennas at the receiver. And that has been repeated now in multiple sessions before, so maybe not wasting time on that. But when you talk about RF impairments, that you have these impairments, they are like chained in different parts of this transceiver chains, all the way from the transmitter side at the digital, all the way through the whole wireless links to the digital side at the receiver. And here there's some very simple example about this kind of a phased array based radio link, very basic building blocks. And if you think about RF impairments, we have quantization noise from the converters. Depending on the transceiver architecture, we may have some IQ imbalance. If we have up conversion by using I and Q signal, we have phase noise from the local oscillator. We have frequency responses of the components. That is also RF impairments. If you have some frequency response that actually causes memory to the signal that you see, for example, in EVM, and you have to equalize that away. Then you can have also beamforming errors. So you have phase shifters that are not ideal. You can have VGAs or amplitude control that is not ideal, and they also causes a little bit impairments to the signal, depending on how you think about. And in the transmitter side, you have also power amplifiers that usually drives antenna elements in these frequencies quite directly. And they, of course, are nonlinear by nature and cause nonlinear distortion to the signal. And in the receiver side, you have plenty of similar effects. You have low noise amplifiers giving adding noise to the signals, like Sumit was talking in the previous talk. Then you have also beamforming errors and IQ imbalance, phase noise, ADC, quantization noise, and these kind of aspects. So these all, they are having impact to the signal quality in the higher frequencies, and most of them doesn't get easier when you increase the center frequency and bandwidth at the same time when you go higher now towards these higher data rates. So these are all important. But if you look these RF impairments in a certain kind of let's say a map where we have, for example, a power at the x-axis, so it could be also, for example, link range, and then we can have signal quality measured, for example, in terms of signal to distortion plus noise ratio. At the y-axis, we see that these different impairments, of course, dominate the performance in different power levels and also in different link distance and link ranges. So, of course, in let's say in these lower power levels, we have a noise limited region where the noise dominates the signal, and then we have some region here where the signal quality is optimized. This was also talked by Sumit in another way, and this region is actually limited by RF impairments such as phase noise, quantization noise, IQ imbalance, maybe frequency response of the components. All those different things, they matter here. They are not that power dependent. And then when you go higher in the power, you will have problems with distortion, either at the power amplifier, but also at the receiver side, you need to deal with these effects. So this all adds up and they create this kind of SNDR behavior of the entire radio link, and every single component there in the chain then matters. Some usually dominate more than the others, but everything here still piles up. Okay, but I said I will focus a little bit more on this transmitter side at the beginning, and namely I will focus a little bit more about due to the nonlinear distortion of the power amplifiers. But if you look the transmitter side, we see that in this kind of a phased array transceiver where we have analog beamforming, we see that some of the impairments they are common for antennas. So if we, for example, take quantization noise of converters or phase noise here, that's common. So that's the same phase noise in all antenna elements, because we divide the signal after this impairment is added to the signal. But then we have some other impairments, for example, now nonlinear distortion caused by power amplifiers, that may have difference over the antennas, because it's different component that adds the signal in each antenna. There's power amplifier in each antenna element. And now the important thing to understand is really this difference. So that's the word I will come back in the talk many times now. So that's something to pay attention. Okay, so if we talk a little bit more about nonlinear distortion in this kind of phased array transceiver, phased array transmitter, we see that there is indeed this kind of common sources of distortion, and then there's a parallel sources of the distortion. And if all the power amplifiers are exactly similar, so exactly the same, and there's no difference in the signal and so forth, then all the sources are kind of common. So you have exactly the same distortion in individual antennas, but that's not usually the case. So there's usually some sort of parallel distortion there, different kind of distortion in different antenna elements. Why is that? Well, first of all, they are different PAs, they are different components, they are different transistors, and they may be variations because of that. But especially in antenna arrays, there's also many other things that has impact. So for example, when you do beamforming, you weight the signals before the amplifier usually. You weight amplitude and you weight phase. Typically more focuses on the phase, but also sometimes amplitude is controlled. And even you wouldn't control the amplitude, you still have phase shifter that has a gain. That gain may vary a little bit as a function of the phase shifter code word, for example, and that has some impact on the signal amplitude, and there's small errors there that actually weight the power amplifiers. So this makes amplifiers, these signals at the amplifier outputs, the distortion at amplifier outputs, to have some differences. Then you may have also different loads. So you have in these high frequencies power amplifiers tries quite directly antennas, and antennas may have differences in the matching. And even small differences there can have impact on the PA behavior when you go to the very nonlinear region. So that may cause differences. And even if that is solved, you have another problem in this higher frequency, because if you don't have isolating elements between the antenna and the PA, the power amplifier in one path, it actually sees signals also from the other power amplifier paths and other antenna paths, because you have finite antenna isolation. So you have coupling, signal leaks from one PA output to another PA output. It modulates the impedance that the PA sees, and suddenly you actually see variations in the PA behavior over the paths in a different way. And then you may have other effects, PAs heat each other and things like this. So there's differences. Again, the word difference is the key. And now I'm interested that how these differences are seen in the radiated signal. So what kind of beam this distortion will actually make. Okay, in order to understand that, we need to understand few basic small things about beamforming. So I'm not going too much on any mathematical things or things like that. I think that there was some discussion about those things before. I have very simple messages here. The first, beamforming is about combining signals over the air to create maxima and to create minima. To have coherent combining and this kind of cancellation combining. Very simple things, fundamental. So indeed, beamforming is about combining signals. And typically when people talk about beamforming, they refer to beam steering. So in beam steering, you make the signals meet at the same time with the same phase in a certain destination so that they combine coherently. That's how you can steer the power. And that's quite basic. And that's done usually in phased array transmitters by using controllable phase shifters. This is something you know. But of course, beamforming is not only about beam steering. You also can control the entire shape of the beam. So for example, you can reduce the side lobes of the beam pattern, and in order to do that, you usually have to control the amplitude also of individual antenna paths. And if you do that, then you can reduce the side lobes as well if you want. So it's not only about beam steering, but it's also about beam shaping. And even further, beamforming is also about making nulls. So you make maxima, you have side lobes, but you also have nulls. And if you want to, for example, minimize interference between two beams, you usually want to do it so that you null one beam from another beam. And in nulling or zero forcing, what you do is that you make the signals meet at the same time, but inverse phase in a certain destination. And with that, then you can create nulls to the beam pattern. But for that, you usually need to control both amplitude and phase excitation over some spatial aperture in a way or another. So simple conclusion from the beamforming. To control or vary the beam shape or direction, one must create differences between the signals in each antenna path. So differences is needed to control that. Okay. So with that, I think we can go to talk a little bit more about the RF impairments in beamforming. And now the question is that, do RF impairments get beamformed? And now first we talk about the nonlinear distortion. Does it get beamformed? And to understand that, let's use example. So now I purposely made very simple example, oversimplified, I would say. 4 antennas, uniform linear array, lambda over 2 spaced antenna elements, and each PA has here a nonlinear model. I will tell it in the next slide. And I will have this 4-element uniform linear array. I will put there a modulated signal, 256 QAM modulated signal at the input. I will go through the amplifiers and see what I see at the output. And then I will do some try to understand what the beam of this kind of antenna array will look like. And in this example, I tried to choose a PA model that is something that is easy to replicate. So I simply use this kind of a RAP, modified RAP AM/PA model, AM/PM model, basically modeling some sort of class A typical compression behavior of an amplifier. So when you increase the power, you will see some compression, and then when you increase the power, you also see phase compressing and maybe varying over the power level. So you will see distortion in the signal when you use this one. So now this amplifier model, 4-element uniform array. Let's play and see what happens. So now when I combine these 4 antennas, four PAs, in the Borel side, 0-degree angle, I will see a spectrum. And of course, because I'm driving the PAs in a nonlinear region, I will see rays in the adjacent channels. So I will see some distortion caused by the intermodulation. And now, this is something like maybe 30 dB ACLR, so not actually that bad. But the point here is that this is a signal that I see in the Borel side. But now what I can do is that I can simulate or plot the beams of the channel power and beams of the adjacent channel power to actually see that what kind of beam this kind of figure of merit that we use to describe the distortion would look like. And then I can understand a little bit how it would behave. And now in this example, I forget to say it, I assume that all PAs are exactly same. So same PAs in all antennas. Let's see what happens. And obviously, because PAs are all the same, distortion level is all the same in all antennas. If I plot the beam of the channel power and beam of the distortion, beam of the adjacent channel power, I will see exactly the same beam shape for the channel power and the adjacent channel power. Okay, small variation here because of the wideband behavior of the antenna array, but from the distortion point of view, same beam shape because PAs are the same, signals are the same amount of distortion. That's obvious. So no differences, beam shapes the same. But next, what I did is that I varied a little bit the compression points of the amplifier just to make a little bit differences there, and then tried that antenna array again in a certain power and see what happens. In the Borel side, I have basically same looking spectrum, so similar ACLR basically when I measure that from the Borel side. But when I go and look the beam shape. So I plot the beam of the channel power and beam of the adjacent channel power. I will start to see differences. So for example, I see higher side lobe level at the adjacent channel power beam compared to the channel power beam. So indeed, there is something happening. Something interesting is starting to happen there. So because there's differences, I will see differences also in the beam shapes of the distortion and signal. So here you see it a little bit better. So case similar PAs, beams of the channel power, beams of the adjacent channel, beam of the distortion and linear signal, they are the same. But in case of different kind of PAs, I will start to see differences also in the beam shapes. So even I don't see big difference here at the actual linear part of the signal. The bigger differences I actually see in the beam of the distortion. So how these differences are seen is now as a different shapes for the beams of the signal and distortion. So now I'm actually now varying somehow the beam of a certain RF impairment, which is now nonlinear distortion. So back to this kind of I like this kind of claims. So let's make one more. So now the claim is that if nonlinearities of individual transmit paths, if they differ from each other, the distortion may have different beam shape compared with the beam of the linear part of the signal. So we learned already from the previously that if you want to control the beam shape and beam, let's say, direction, you need to create differences in amplitude and phase. So it's the same thing here. If you want to control, or if you want to understand how differences in the amplifier behavior, for example, is seen in the radiated signal, the differences are the key there. Okay. So with this in mind, we go forward and we talk about what happens when you take this kind of antenna array with multiple amplifiers, multiple sources of nonlinear distortion, and you try to linearize that. So we talk about this kind of array level mitigation of RF impairments now from the nonlinear distortion perspective. And furthermore, we talk that from the digital pre-distortion point of view. So now I assume that I use digital pre-distortion as a linearization technique. And just as an overview, that's very basic. Linearization techniques used a lot in power amplifiers. That's very nice because you don't have to worry about the amplifier itself so much. All you need to do actually is that you measure the amplifier behaviors. You measure the output signal of the amplifier with some sort of a feedback receiver. And then when you have measured that, you fit a model that models the whole transmitter path and its nonlinear distortion, and then you fit the inverse of the nonlinear distortion. You feed it to the input, and then you achieve linear signal at the output. So you pre-compensate the distortion of the signal. However, how you let's say use this DBD for antenna array, you have to think about the concept a little bit. So this becomes interesting usually because you actually have one DBD input, but you have multiple nonlinear power amplifiers in parallel. So one DBD is the multiple power amplifiers here is sharing a single DBD. And in these cases, you have to think about this DBD concept again. You have to think about that what you actually linearize. Shall I linearize one amplifier, or shall I linearize maybe the worst amplifier, or I make some sort of average? Sometimes things like this is done. But you can also do something else. You can actually linearize the sum of the amplifiers. So you can linearize actually the signal, the system in beam level. It's also called beam-oriented DBD or array DBD. Different kind of ways you can do. There's another problem. Another problem is that in order to linearize this kind of system, you have to also measure the amplifiers, and that's quite challenging in phased array, especially if you have highly integrated system. And there's a lot of work people does in the literature regarding that, and including also our own work. So if you want to know more about this one, you can take a look, for example, my thesis, and then many other works that actually I refer also in there that is doing a lot of different kind of approaches there. I'm not talking about that today. I'm interested on this box here. So if PAs are different, we learned that there's some impact on the beam of the distortion from these differences. And now I want to see that how that looks like if I linearize the system, if I linearize the transit, the group of amplifiers by using DBD. Let's see. So I take the same example, 4 power amplifiers, 4 antennas, and case exactly the same PA for all antenna paths and a bit different PAs for different antenna paths, and see what happens. So obviously, if I have exactly the same amplifier in all antenna paths, if I do linearization, I will see linearization in all angles. So I will actually see the whole beam of this distortion, beam of the adjacent power going down, but the shape will remain because the PAs are similar. So there is nothing actually interesting happening from that point of view. This is of course good. The whole beam goes down, but usually the PAs are not exactly the same, and that goes us to the second picture here. So now we learned previously that when we had differences, the beam of the distortion was different from compared to the linear signal. And now if we take this one, combine it, we linearize it by using DBD by using the whole over the receiver. Now in this case, we see that the beam of the distortion is totally different. So we actually start to see a null in the distortion in our steering angle. So we actually zero forcing the distortion in space in this kind of thing. And all we actually did is that we applied the common DPD for all the antenna paths. And that why this happens is that the PAs are different. None of them are actually very linear, but as combined, they are linear. So there's some sort of over the air linearization effect happening. So with array DPD, these small differences over the PAs, they create major differences in the beam of the distortion. Okay, we have done a lot of work on these things in the past here, and there's also plenty of other good work from different universities all over the world. I picked here just a few examples. So this is one paper where we actually demonstrated this kind of over the linearization in 2019. So here what we did is that we had a 28 gigahertz phased array transceiver. There's a 16 gallium nitride PAs here under the antennas. And what we did is that we just put that in the lab. We placed that on the rotary table. We took a reference antenna about 2 meters from the phased array, and we feed the modulated 5G NR signal to the array input, and we measured that by using this reference antenna, fed that to the signal analyzer, and then took that back to the MATLAB and designed the DPD for this oral array with some basic memorable polynomial. Very simple example actually from that point of view. And then we just see what happens. And what actually happens is that we can actually illustrate beams of the signal and beam of the distortion together with the DPD. So now in this picture, we see measured beam of the signal and beam of the distortion, the beam of the adjacent powers. And now the beam of the signal is quite nasty. So this is not nice looking beam. This is not very well calibrated array. And that's for the purpose because there is differences now that we can actually demonstrate this effect. And now what we see is that indeed when we linearize this kind of array, so these solid lines are the ACPs without DPD, and dashed lines are the ACPs with DPD. So we see that actually indeed there is something here happening. So there starts to be a null, kind of a null in the distortion in the steering, but not very deep one. We could get it deeper if you could get a little bit better DPD performance, but we see actually this kind of over the air cancellation happening. And you see it that much better now when you subtract the ACP from the channel power, so you calculate the difference called ACPR. In ACPR, you see that kind of null actually happening here, but here you actually see from the principal point of how it should look like. So indeed, now DPD does have impact on the beam of the distortion. So even we apply the common DPD for all the antennas, we shouldn't basically make any differences over the antennas. We actually do differences because we have nonlinearity. And that's nonlinearity now makes this kind of effect. So now we can say that DBD performance in this kind of array, that's direction dependent. That's important thing to remember. So to conclude from this part, we can say that linearization by beamforming is about nulling or reducing distortion in a certain direction or position by combining multiple nonlinear components over the air. So there's some over the air linearization as a part of the process here happening. Okay, let's look few more examples. So this is one old example from the past, which is actually illustrating quite well that what is actually happening in this region where we have this over the air linearization done. So here in this example, what we did is that we had a amplitude tapering. So we were having same power amplifier in all antenna paths, but we were weighting the individual input amplitudes in order to reduce the side lobes of the beam pattern. And the PS were following this kind of model, and then we applied these input powers. There was some, I think, 256 QAM signal there at the input, and then we can illustrate what happens at the output. And these are now AM models, AMs together with DBD of this kind of individual PA paths now in a certain steering angle where we looked at. And here we see what actually happens is that in this kind of case, none of these amplifiers are really linear. So here it's okay, but if you go to the higher power, you will see that some of the PAs, the higher trio ones, they compress. So they are actually non-linear, but there also these lower trio ones are non-linear together with the DBD when you cascade them. So because they expand, because DBD focus more on this higher trio PAs now. So in this domain, the distortion sign of these amplifiers, it's inverse to the distortion sign of these amplifiers, and they cancel each other, and you create this kind of over the air linearization effect. So you can call it linear amplification with nonlinear components, or you can call it feed-forward linearization, or whatever you want to call it. There's maybe I don't know what is the right name here, but the point is that there's cancellation happening here, and this cancellation is the one that creates the null. So it's zero forcing the distortion from the spatial point of view. Okay. So now we can understand already that if we want to have this kind of omnidirectional linearization, so good linearity in all angles, we have to have similar amplifiers, similar impairments over the antennas. And if we still want to control the beam shape by doing amplitude control, we have to do something. And one way to do that is to use PA bias control. So basically control the amplifiers. And we did that in one example so that we actually took this 28 gigahertz gallium nitride phased array, and we actually controlled the bias points of the individual amplifiers. We measured them in all different gate biases, and then we modeled them how they behave with different biases, and we tried to find bias points that actually gives a similar let's say nonlinear behavior for different amplitudes. And actually we were directly controlling the power by using this gate bias of the PAs. And this was actually interesting because it actually did help in the linearization. So here is simulation results still, but you see here is that the biggest differences here between different techniques, it was not in the AM, but it was in AM/PM. So when we controlled the bias points of the individual amplifiers, we were actually controlling quite strongly also the phase of these individual amplifiers. Then we had to compensate that with the phase shifter with some external calibration. But after we did that, we were actually able to achieve quite linear AM/PMs for individual amplitude levels. And when we then took this one and linearized the common effect, we can see that actually we had quite good omnidirectional DBD performance. Compared to the fact that if we would driven the similar PAs with different input amplitudes, so we wouldn't have this bias control here, we would achieve very directive linearization because they had to cancel each other in order to make a linear output because there's not so much common distortion happening there. Okay, this was also measured in the lab with similar example. So we were measuring the beams of the distortion with different let's say the side lobe level targets, and we were actually then also integrating this additional power over the entire space to measure this kind of a total radiated ACPR, which is something that actually they specify nowadays in 3GPP. And we were actually seeing that indeed with this kind of technique you can achieve total radiated linearization if you want to do that. So you actually have to control the amplifiers in order to achieve this. Okay, so from this point of view, we can say that there is some sort of trade-off now. So the trade-off is now so that if we have any differences, we can harness the differences to cancel each other and make this kind of combined linearization. So we can even gain from the differences. But on the other hand, if we have exactly similar, we can have a good overall linearization performance. So more differences, more we can boost the common effect, so more we can make them to cancel each other. But actually the problem is that the distortion has to go somewhere. So if we make a null somewhere, the distortion will spread elsewhere. So we are actually creating even more distortion sometimes in this kind of example. So this is one of the trade-off here in the array linearization that one must consider. There are also others. There's more examples, more information about this kind of trade-offs in a book that you can look. But let's go forward. So what about all other RF impairments? So now we talk more about nonlinear distortion, but is there something also from this that we can take away when we talk about other RF impairments? And indeed we can. So, well, okay, this is maybe some random table, but actually we can benefit in array level almost in all RF impairments if we think about that in the transceiver architecture. So of course, quantization noise we can benefit if we have multiple parallel converters. We can benefit from this array effect if we do some tricks. Thermal noise, well, that's used all the time in the receiver. Receiver nonlinearity, even in principle, we can do that as well. It's not that simple, but there are some methods. Nonlinear distortion we talked about, but also phase noise. If we have independent local oscillators in individual antennas, we can benefit from the averaging effect because there's differences in the bands. So similar thinking applies. Maybe the differences are a little bit differently taught in different RF impairments, but same kind of effects is there. So I will show you a few examples. One example is reduction of ADC quantization noise in array level. So if you look at this kind of more theoretical domain papers, beamforming papers, digital signal processing papers, what they do in communication society, there's a lot of discussion have been already 10 years about low resolution ADCs. And that concept, it's based on the point that you actually use differences to randomize the quantization noise over the antennas, and then you can get the combined effect in averaging. And that kind of technique is used a lot in ADC design as well. So if you have multi-channel, multiple parallel converters, and if you add noise to the signal before the conversion, you can use the noise to randomize the quantization noise, and then you can get benefits when you combine, so that the quantization noise is actually more uncorrelated, and you can get averaging gain. And that's actually dithering. Dithering is the word that they use quite a lot. Okay, I just made for this simple simulation here in MATLAB that indeed actually in this case, if you have a certain number of antennas, and I just put the four element ADC simple model there, you see that there's a certain SNR level at the ADC input where you can get the best gain out of this quantization noise averaging. So actually what happens is that if you have too much noise, okay, you are noise limited. If you have too good signals, so if you have let's say too good signal to noise ratio before the quantization, you will also lose, because then the quantization noise will dominate. But there's some optimum point where this noise can randomize the quantization noise and you get this benefit. This is called stochastic resonance in the literature related to the low resolution ADC. But similar effect. Noise makes differences. You add the differences and you can gain. Okay, same thing can be done for phase noise as well. So if you have, I will just go through. So if you have a same LO for all antennas, you will have a certain EVM. But if you actually have different LO, so this is now only with 2 antennas. If you have different LO for individual antennas, and you have some let's say a little bit uncorrelated phase noise sources there, you can of course get benefit from that effect, but that will cause some other problems that you need to deal with. And again, the key is the difference. If there's differences in the impairments, you can gain from the array effect, because beamforming is about summing, and if you sum differences in uncorrelated way or in cancellation way, you can get benefits. So the key is in the differences. And that brings me to the conclusion, which is this one slide. So the conclusion is that if the RF impairments of individual transit paths, if they differ from each other, the figure of merit to measure the impairment may have different beam shape compared with the beam of the ideal part of the signal. So differences can be used in advantage in this case. Okay, well that's all I basically have. As a conclusion, maybe I can acknowledge the many projects we have been doing around these ones, and also thank the whole let's say 6G flagship team, but especially team that has been doing these transceiver linearization topics and signal processing topics together with us over the years. So thank you, and I think we can conclude this one.
Yeah, thank you, Nuti. It was really good talk.